review for our little quiz on climate change, the ozone layer, and acid rain. Let me just kind of show you a couple of our movies that or a couple of our movies of a couple of our labs that we had done. So this one here was really just that smog in a jar. And if you remember, we really could get nitrogen oxide. That's kind of that yellow smoke you see, that smog you see forming in the jar there. And we add a little bit of water to that. If you remember, we could notice that as water mixed with that, it caused our cabbage juice to change color. But it was really just kind of some easy evidence of how some of these chemicals we put into the atmosphere can make the water become acidic. Now, really a kind of a point I tried to make as we went through these last couple of weeks was a lot of these chemicals that make the water and the water cycle acidic are naturally occurring. So when you hear about, causing acid rain or pollution, smog causing climate change, I think it's important to remember that there are natural sources of these same chemicals. So, but yeah, this is just kind of a simple way of how you can think how the exhaust from a car, from an automobile, gets pushed out into the atmosphere. It mixes with the water. And there you can see our cabbage juice did indeed change color. It's really kind of similar when I put carbon dioxide into water. And we watched our indicators change color there too. So another kind of activity we did I thought was worthwhile was looking at what it means for a catalyst. So a catalyst to increase the rate of a chemical reaction. The one we talked about in class was really what chemicals deplete or catalyze the depletion of the ozone. So it's important to remember that the ozone layer naturally is kind of reaching a balance and decomposing. Just like our hydrogen peroxide will naturally kind of decompose. Now we added that black powder. That black powder was a catalyst. And it kind of accelerated that decomposition of the hydrogen peroxide. But yeah, our evidence for that was really that there was a lot of hydrogen and oxygen being given off as it decomposed. And our evidence for that was the fact that that pure hydrogen, pure oxygen would catch on fire a little bit more easily. So that atmosphere, the air inside that test tube was a little different than the air in our classroom there. But yeah, that was the good evidence that what it means for something to be a catalyst. And now the thing is some of these same chemicals that catalyze the decomposition of the ozone are some of the same chemicals that contribute to climate change, some of the same chemicals that contribute to acid rain. But once again, keep in mind there are natural sources of those. So yeah, so thanks for your time here as we go through this. Really what helps, I'm hoping you've kind of looked at that quiz review, and I'm just going to kind of go through these topics and a lot of these questions with you here. So climate change. What's our evidence that their climate on the globe has been changing? Well, really, it's we correlate it with these CO2 levels, I guess is one thing. So I'm hoping you've kind of seen this type of graph before, but the whole idea is that this red line on here is how much carbon dioxide we've been able to monitor in the atmosphere. This black line kind of represents these temperature fluctuations we've seen on average on the globe. Now, what's remarkable is you see this, there is really as the carbon dioxide levels go up and down, the temperature levels correlate with that and go up and down almost at the same kind of rate. Now, what's fascinating to me is that these numbers go back like a million years. 800. We didn't even have thermometers a million years ago. We're not even sure if there was really people. So, the whole thing is we don't really know what the temperature was a million years ago. But we've been able to kind of correlate this global temperatures with the way the ice formed in the Arctic region. So when you look at data or hear about what the temperature on Earth was millions of years ago, I think it helps to kind of think about that in terms of they're monitoring or they're digging up these ice core samples, and based on the way the chemicals formed and the way the ice formed, they're kind of able to determine what these global temperatures were. But really, it's really only in the last 100 years or so, 150 maybe, that we've really been measuring temperatures all over the world directly. Along with CO2 levels, we've only been measuring or monitoring those directly for the last 100 years or so, not the last million years. So when you see data that goes back like almost a million years, just kind of keep in mind it really is kind of measuring or looking at what's in these ice samples, and we can kind of determine what the Earth may have been like a long time ago. Yeah, here's one from not a million years ago, but like 20,000 years ago, but same thing. You know, people weren't writing it down then. We didn't have thermometers invented then. But just another way to see here, the red is the carbon dioxide levels in our air, in the ice samples. And then here's what we were able to kind of determine for temperature levels. So we do see this direct correlation between temperatures and carbon dioxide levels. Now, we have been monitoring or measuring carbon dioxide levels directly. And here's one since 1950. So since 1950, we've kind of been able to, well, here's some global average amounts of carbon dioxide in the atmosphere, and that tends to, remember, strongly correlate with our average temperature levels. And what makes that ice core data kind of reliable is just the idea that when we overlay ice core data with direct measurements, in other words, just going outside and really monitoring how much CO2 is really in the atmosphere, the ice core samples and the direct monitoring are right spot on. So that's what kind of gives us that confidence to say if the ice cores are indicating there's this much CO2 50 years ago, then maybe that's still a reliable way to look at the CO2 levels a million years ago. Now, so the question is why is CO2 contributing to climate change? And we'll get to that here in a second. But another thing with the carbon dioxide, and it's not just carbon dioxide that contributes to climate change, it is a big one. A couple other chemicals that contribute to it, methane can start to absorb some of this radiation in our atmosphere. Then nitrogen oxide, that smog in a jar, that's another molecule which can absorb some of this radiation from the sun. So when we talk about climate change, really what we're referring to is the molecules in our atmosphere have this ability to absorb radiation, and as they absorb that radiation, that tends to make the troposphere warmer. And it's not always just warmer, but sometimes it results in a bigger fluctuation of a change in temperature. But yeah, so I mean, I think we've kind of heard this a lot, but where is all this carbon dioxide going and where is it coming from? Well, certainly there's natural sources of it. People breathe out carbon dioxide. Animals push out carbon dioxide. Bacteria are pushing out carbon dioxide. But we do burning fuels increases the amount of carbon dioxide in the atmosphere. Now, where does it go? Well, a lot of it settles into the oceans, it settles into the ground, it just mixes with the water in our atmosphere. And so every time we push out carbon dioxide, it needs a place to settle or a place to go. And that's why we see a lot of these kind of chemical reactions written with two arrows, is we're always kind of trying to discuss any reaction with water. We always try to discuss or indicate that there's a balance achieved, an equilibrium established. And that's why we saw a lot of our chemical reactions with two arrows. Where's it going? What's it turning into? And we kind of reach that balance. And so yeah, there's sources of carbon dioxide and places for it to go. There's sources of the nitrogen dioxide, places for it to go. Sources of sulfur dioxide and places for it to go. But a place that a lot of it goes is our atmosphere, and really what it sticks to or mixes with or blends well with in our atmosphere, or what it establishes an equilibrium with in our atmosphere, is water. Okay. All right, so the water. Well, we'll look at our water in a minute. But as we look at our water, I think it's real important to remember that it stays in our troposphere. All right, the water cycle, it just gets too cold as we get above Mount Everest for water to really escape into those upper levels of our atmosphere. So as all of this sunlight comes down, and really you can think of the radiation from the sun as really just about anything on this spectrum. That's fair for our purposes. You know, a lot of times we think ultraviolet is just sunlight, but really the sun has visible light. There's X-rays, gamma rays, infrared. This whole spectrum, you could argue, is being emitted by the stars, emitted by our sun. This whole spectrum of radiation gets to Earth. Now, what happens when it gets to Earth? Well, some of it's absorbed by those molecules, but before it filters down to the surface, it has to go through all that radiation. Think of it as light. It has to go through all these layers of our atmosphere first. What really makes the weather, or really causes climate change, is just, well, what's going on with the radiation that gets down here to the surface? Well, I kind of want us, and this is kind of a complicated diagram, but I kind of want us to be able to look at this and notice, okay, a lot of this sunlight, that's just this yellow, if you look at this, is 342 watts per square meter. It's just really how much energy per unit of area the sun's kind of emitting as it gets to our atmosphere. But if all this sunlight gets up here, not, like 342 watts per square meter, about 168 watts per square meter will actually hit the surface here. So some of it's reflected by the clouds. A lot of it's absorbed by these layers of our upper atmosphere, especially all these harmful types of radiation. A lot of those harmful type never really reach the surface. But when this radiation does reach the surface, whether it's the plants, the soil, the concrete, the rocks, whatever it is, it's as that radiation hits our ground, after it's absorbed, the infrared is what's released. So, and it's that infrared that's reflected by the surface, that's infrared radiation. Infrared, infrared, infrared. Carbon dioxide is good at absorbing infrared. The sulfur dioxide is good at absorbing infrared. The nitrogen dioxide is good at absorbing the infrared. So when we talk about warming of our atmosphere or the greenhouse effect, it's really just the sunlight reflecting or re-emitted by the surface is infrared. And then that infrared is absorbed by the carbon dioxide, the nitrogen dioxides, the sulfur dioxides, but the thing is, even water's going to absorb some of that. So, okay, so that's really kind of what this whole thing on climate change is referring to. Our evidence that the global climate has been changing over the last million years comes from ice core data. The temperatures that we feel on Earth is a result of infrared being absorbed by those molecules in the troposphere. And the infrared is what's being emitted from the ground or reflected by the ground. All right, now the ozone, all right, so we've heard of the ozone depletion having a role in climate change. Well, what ozone depletion does is if the ozone wasn't there, a lot of this radiation, more of this radiation would hit the surface. So if more radiation hits the surface, more infrared is reflected by the surface. The ozone does a great job at protecting us from all of those harmful types of radiation. So yeah, it blocks these harmful UV types of radiation. It absorbs, it's kind of, just a simple way, it's the Earth's natural sunscreen. About 95% of the sun's radiation is blocked out by the ozone layer. Now remember, the ozone is above the troposphere, it's in the stratosphere, so this is above Mount Everest. But yeah, the Earth's natural sunscreen, filtering, screening out, blocking 95% of the sun's radiation. That's awesome. That's a great way to think of the ozone layer. Now, as O3 turns into O2, as it starts to break down, what catalyzes that breakdown of ozone is water. are nitrogen oxides, like our smog in our jar. And another one that catalyzes the depletion of the ozone is methane. Methane's a natural gas. Now, water, remember, even though we consider water very natural, the water that gets up to the ozone layer is because we carried it up there. It doesn't naturally get up above Mount Everest. It's too cold. So if water is going to deplete the ozone, it's water from jet fuel, water from rocket fuel, their exhaust that we've carried up there. But once again, what depletes the ozone, or what catalyzes the depletion of the ozone is water, methane, or nitrogen oxides. And then some of these are called halocarbons, but we've done a pretty good job at removing those from aerosol cans and refrigerants. So they aren't as significant as ozone depleting chemicals as they were 15 or 20 years ago. But yeah, so the ozone layer, it's in the stratosphere. What is it composed of? O3. What role does it have for life on Earth? It's the Earth's natural sunscreen. What are 4 catalysts that contribute to its depletion? Water, methane, nitrogen oxides, and then those chlorine, fluorine, bromine, those halocarbons could also be considered a catalyst for ozone depletion. Okay, now these molecules that are in our atmosphere, they naturally are going to mix with water. Anytime you add chemicals to water, you start to affect the pH of the water. If you start to lower the pH, we say that starts to make the chemical become more, or the water starts to become more acidic. So let's take a look at that. Now, once again, the water cycle really is very easy. It's just that water evaporates and water condenses. And once again, the clouds get, that's the level, really the top of the clouds. You can think of that as the top of the troposphere. That's as high as water will naturally get. I think something that's real important to kind of recognize about the water cycle and climate change is that when the water's evaporating, that tends to cool the surroundings. Just think of stepping out of the shower or sweating. Why do we sweat? Why does water evaporate off our skin? Well, as the water evaporates, it takes in energy. It takes in heat from the surroundings, which allows the surroundings to get cooler. And then the opposite, when water condenses. So think of that kind of up in the upper levels of the atmosphere. That condensing of water vapor releases energy and tends to warm the surroundings. So really a lot of our weather, a lot of our temperatures that we feel, I just want to make you aware it's not just solely due to climate change or radiation. That's certainly a big part of it, but just water's own natural processes tends to kind of reach a balance or affect the temperature in our atmosphere as well. Okay, so as these chemicals we put into our atmosphere start to affect the water, we notice that with color changes, all right? And that's really kind of how we monitor pH. So understanding pH, we made our pH indicator with cabbage juice. We saw we can mix things with the water and get the cabbage juice to change all of these colors. There were some other indicators we brought in and kind of played with. But yeah, let's take a look at this pH scale here. Yeah, now, and I also want you to understand, besides just this understanding the pH scale, I want you to be able to look at and know what a titration is all about, which is kind of one way that we can determine how strong or how concentrated an acid is. Is it something like battery acid, or is it going to be something like coffee? And then you can see acid rain and coffee are about the same there. Okay. Okay. Now, we say 7 is kind of that pure water, but really remember water can kind of shift its pH based on what chemicals are added to it. Now, if we add carbon dioxide to water, it makes it more acidic. Think of soda. All right, part of what makes your cola, your soda, acidic is the carbonation. The nitrogen dioxides, that smog in a jar, that can make water acidic. sulfur dioxide. We didn't really burn up any sulfur in the room, but sulfur, what kind of comes, another thing that comes from pollution and exhaust and burning fossil fuels, that tends to mix with water and lower the pH as well. But yeah, okay, so if we add chemicals to water that make it acidic, the pH gets lower, further from 7. Now what we did in our titrations, if you remember our burettes, we would put a base in there. Now the base that we used was pretty much just like soapy water. So we were right about here, 9, 10, this kind of soapy water is really what we had in our burettes. And then we even brought in some rain from St. Louis, and the idea was as you add your soapy water to your acid would, the pH would go up, and then we could see that distinct color change occur as you titrated your base down into there. So if it took a lot of base to neutralize it, we said we're starting with a stronger acid. If it took just a little bit of base to neutralize it, we said we were starting with a weaker acid, or an acid closer to 7. So how much base, how much soapy water it took to change the color of your acid, to neutralize your acid, was one way to measure how strong that solution of water, that acid, really was. As we get closer to 7, the acid concentration decreases. So yeah, here's a great question here. Let's just say this is kind of a simple way to think of it. What if your acid was what if your water was 1% acid? Well, 1% is 1/100th. 1/100th, 1% is 0.01. 0.01 is the same thing as 10 to the minus 2. And remember, it's that exponent, that negative exponent, is what the pH is really measuring. So water has this natural ability to kind of have this low concentration, this 10 to the minus 7th concentration of acid in it. That's just kind of what water naturally does, and that's where that pH of 7 comes. As we add things to water, we disrupt that equilibrium. Things like carbon dioxide lower the pH. Things like nitrogen dioxide lower the pH. Sulfur dioxide lowers the pH. Now, it's not always bad, because remember, a lot of stuff likes acidy soils, or a lot of fertilizers can kind of make soils and stuff more acidic. So it's not all, I mean, normal rain's about a 5.5, 6. It's not really technically acid rain till it's below pH 5. Okay, so let's take a look. What did we say here? Recognize the causes and effects of acid rain. That's just adding chemicals to our atmosphere that make the pH go down. Carbon dioxide, sulfur dioxide, nitrogen oxides. How do we measure pH? With indicators with color changes. As pH goes down, concentration of the acid goes up. And then once again, be able to predict relative amounts of base needed to neutralize acids in a titration. In other words, if it takes a lot of base, it's a strong acid. If it takes a little bit of base to neutralize it, it's a weaker acid. All right, let's go through these questions. Let me just kind of read them to you. I hope this is worth your time. Types of radiation. All. That's fine. If you just started listing any of these types off of there, I like it. What is absorbed by the plants in the ground? UV, even our skin. I mean, the stuff on the ground absorbs that ultraviolet. And then it's re-emitted as infrared. So we absorb the ultraviolet and we re-emit the infrared here on the surface. Which type of radiation is absorbed by gases in the atmosphere, which warms the planet? That's also infrared. Evaporation, that's going to occur in the tropics, near the oceans. What happens to the surrounding temperature as water evaporates? The surroundings get colder. Up in the upper levels of the atmosphere, as the water vapor naturally condenses, that tends to make the surroundings get warmer. I just can't, when you talk about global temperatures, I just can't forget the effect that water has just on its surroundings. It's not solely radiation. A lot of the temperature that we feel is also due to what water is kind of a naturally changing phase there. When we talk about global or climate change over the past million years, remember it's always kind of ice core data that we're using that correlate strongly with temperatures. What do people say causes our climate change? Well, if we as a civilization, as humans, are putting off more carbon dioxide into the atmosphere, then there's more absorption of the infrared, which does tend to make the temperatures fluctuate more, which is what we say climate change is being caused by. Another maybe cause of climate change is ozone depletion. Remember, ozone is O3. The O3 is formed by just normal O2 and radiation, sunlight, mix or react, form O3. But once again, that really only happens up in the ozone layer, which is in the stratosphere. Now, some of that O3 it naturally decomposes. There are chemicals which catalyze that decomposition. Those chemicals would be the water, the methane, and the nitrogen oxides. What is the barrier between troposphere and stratosphere? It's called tropopause. That's kind of, you get above the tropopause, that's where you start to get into the ozone layer, the layer where O3 exists. Once again, water doesn't naturally get into the ozone layer. So the water that's there catalyzing the ozone depletion is jet fuel, rocket fuel. The other catalysts can kind of naturally get up there. Methane can float up there. Nitrogen oxides can float up there. And even some of these halocarbons can float up there as well. As we talk about, remember how water can, evaporation cools the surroundings, condensation warms the surroundings. Remember, most all the water, I think we know this, is in the ocean, a little bit frozen in those ice cores and those glaciers. And then really the water that we use and the fresh water in our atmosphere and the groundwater is really just a small, small percentage of the water on Earth. Ozone depleting substance, remember that's a catalyst. It just speeds up a natural process. As the ozone depletion speeds up, more radiation gets in, more infrared can then be re-emitted, which means that there's more carbon dioxide, more infrared. That does tend to cause our climate to change. P8, we talked about this. St. Louis, it's about a 4.5. Columbia, Missouri, Iowa, about a 5. Ohio, a little bit lower. And we're about the same as New York in terms of rain. And I think that's what we saw just kind of when I brought in some rainwater. You guys really is right about the same as the coffee. It's a good way to think of our rain. Really, okay. So hopefully you can kind of look at these exponents. Just correlate that negative exponent. That's the same as the pH. All right, that negative exponent of 10, that's the same as the pH. It's the same as the concentration. And it's these color changes, these natural color changes that we use to kind of determine that pH. Once again, if it takes a lot of base to neutralize it, it's the strongest. If it takes a little bit of base to neutralize it, it's the weakest. Okay, and then some of the chemicals, I'm hoping this was easy after playing around, but we all know water. I think we all know carbon dioxide. If you know carbon dioxide, it's easy to get our sulfur dioxides, our nitrogen oxides. I want you to recognize ozone, it's O3. Methane, natural gas, CH4, and then once breathable oxygen. So a few chemical formulas there, but I think it's not too bad, especially after you got a chance to kind of use a lot of those in class. I hope this helped answer. Please ask me questions. I want you to do well on this quiz tomorrow. Thanks for listening.